The NIST sphere devices provide uniform light intensity. The 2-meter sphere has 32 exposure chambers with 5 mechanical load chambers. This includes 4 multi-sample sealant chambers and 1 modified conventional chamber for single sample testing, which has a 1,000 Newton option. There are several sample holder designs, but a 17 specimen holder is typical. Neutral density and bandpass filters prior to the specimens are used to adjust the incident irradiance intensity and light spectra. The multiple chambers on the 2-meter sphere allow for simultaneous multivariate experiments for a truly high-throughput design of experiment. There are 2 half-meter sphere devices, a 6-port sphere and a mechanical sphere. The 6-port sphere provides up to 6 environmental chambers with temperature control from 30 to 90 degrees Celsius and relative humidity from 0 to 85%. The UV irradiance of the smaller sphere devices, which have 2 UV lamps compared to the 6 UV lamps that the 2-meter sphere has, is around 700 watts per meter squared, 4 times greater than the 2-meter sphere. To get broader adoption of the NIST sphere technology, a smaller, more economical device was developed to bring the NIST sphere directly to industrial partners. A commercially viable device, the half-meter sphere, incorporates the knowledge gained from operating the 2-meter sphere for over a decade. The half-meter mechanical sphere allows for 8 simultaneous mechanical tests at 1 environmental condition.
Here we have our group's QUV exposure system. While the sphere is our workhorse instrument for UV weathering studies, the recent addition of the QUV system in spring of last year has expanded our aging capabilities. As well, this system is utilized in a variety of industry labs to examine the aging of various materials and products. With this exposure system in-house, we can now perform comparative aging experiments to quantitatively evaluate similarities and differences in aging behavior of materials exposed in the sphere versus QUV.
The IMG group has several environmental chambers with temperature and humidity control. The 4 large walk-in chambers are used for storage and cure of concrete and fiber-reinforced polymer composite, or FRP, bonded to concrete. Cure of specimens designed to undergo the alkali-silica reaction, operation of the VICAT apparatus to collect cement or mortar set time data, and sulfate expansion studies.
The Infrastructure Materials Group, or IMG, has a suite of sample preparation and characteristic tools to evaluate a material's chemical, morphological, structural, and mechanical properties. It is one of the most complete polymer and materials characterization laboratories at NIST. This asset is often utilized by multiple NIST labs and outside collaborators. Sample preparation methods include plasma etching and sectioning using a cryromicrotome for material cross-sectional analysis. Specimens can also be examined optically with conventional microscopes. Physical properties of materials have been measured using moisture sorption analyzer and contact angle devices. There are several spectroscopic methods that are used in IMG. Fourier transform infrared spectroscopy is a workhorse for monitoring changes in chemical structure of materials in our degradation studies. FTIR produces a characteristic spectrum on the bonding environment and is well suited for analyzing materials to changes and differences in bonding after degradation. Another spectroscopic method that is employed is ultraviolet visible UV-vis spectroscopy. UV-vis techniques measure materials degradation by quantifying the extent of yellowing and other color changes with the absorption or reflection in the visible range, and is often correlated with the types of bonds and other functional groups in a material. We have microscope versions for both FTIR and UV-vis that allow for transmission and reflection mode analysis. Finally, a variety of thermal properties of materials are examined using differential scanning calorimetry for changes in glass transition temperature of polymer materials, for example, and thermogravimetric analysis to monitor weight loss as a function of temperature. Material property changes as a function of temperature can also be examined using the dynamic mechanical thermal analyzer.
In this room, we have several instruments that comprise our mechanical testing capabilities. First, we have our MTS Criterion 45. This instrument is utilized in several projects, perhaps most notably a collaborative study of cable aging performed with the Nuclear Regulatory Commission. The physical size of this instrument permits cross-head extensions of over a meter. This capability, along with its 10 kN load cell, allows for the study of mechanical performance of a variety of materials, and in particular, those with very large strains, such as polyethylene or polypropylene. This is our servo-hydraulic instrument. This versatile instrument permits a variety of static and dynamic high-force testing studies to be performed. Next, we have our microtester. As we will see in a moment, the microtester is used for digital image correlation, that is, DIC, measurements. Here, we see our microtester in action as seen with the naked eye. And here, we have our DIC setup along with DIC acquisition as a sample is tested. With DIC, we may resolve the distribution of stresses and strain within a sample as force is applied and observe its evolution over time, providing key insight to the mechanical failure modes of a material. And last, we have our custom sealant testing setup, which is utilized to carry out ASTM C1735. This nano characterization lab has 4 different instruments: the nano indenter, the laser scanning confocal microscope, the Raman microscope, and the atomic force microscope. This G200 nano indenter has 2 instrumented indentation testing modes, XP and dynamic contact mode, DCM for short. The max load for XP is 500 millinewtons, and DCM is 10 millinewtons. We use XP mostly, and a high load option can be added for future capabilities. Using continuous stiffness measurement mode, CSM for short, Young's modulus and hardness can be obtained from the load displacement curve. Typically, we characterize surface mechanical properties by indenting into the sample's top surface from 5 nanometers up to a few microns. We can also indent across a cross-section sample. We have done this for materials such as multi-layered samples like a photovoltaic backsheet, concrete with various aggregates, or photodegraded specimens. This was done to map the modulus and hardness of each layer or region and the interfaces between. We have demonstrated nano-indentation as a very powerful tool for conducting depth profiling of mechanical properties of polymeric materials after increasing or various periods of UV-induced degradation. Moreover, we have successfully correlated the results, a modulus map, to chemical measurements, as obtained with FTIR. The laser scanning confocal microscope, LSCM for short. Here, our model is the Zeiss LSM 800. Operating in reflectance mode, it is a fast microscopic technique compared to SCM, suitable for surface and subsurface morphological mapping, and quantifying or detecting microstructures and the heterogeneity of a material. For example, is applicable for samples composed of different pigments and particles, or crystalline structures. In general, laser scanning confocal microscopes collect reflected light specifically from the focal plane and generate a stack of optical slices at different Z positions. 3D rendering images and surface roughness can be obtained at multi-scale scanning areas. One other important attribute of this microscope is that the sample stage can sustain a heavy load without affecting image resolution. We can conduct fragmentation tests of photovoltaic backsheets using a mini-tensile tester under the microscope. In this unique operation, and our industrial partners and collaborators, DuPont and NREL, have implemented similar approaches based on our setup. Raman spectroscopy is a powerful spectroscopic technique used to probe the chemical bonding environment of materials. This Bruker Centera XL Raman microscope was recently purchased in 2019. This system is equipped with several lasers to excite and characterize the samples. Confocal Raman will be used for depth profiling and failure analysis of exposed laminated multi-component photovoltaic backsheet coupons, and the results will be compared to that using other scanning electron microscopes. Atomic force microscopy, or AFM for short, is commonly used to measure surface morphology in nanoscale resolution. It operates in contact, tapping, height phase modes to characterize surface topography and morphology. Our AFM, a Bruker Dimension Icon, also has the capability to perform in peak force quantitative nanomechanical mode, or PF-QNM for short, for elastic modulus measurements and an electric force microscopy EFM mode. We have a liquid cell for studying tip and material interactions in the liquid environments.
The microstructure laboratory has 2 X-ray powder diffractometers and 1 3 kilowatt wavelength dispersive X-ray spectrometer. The newer XRD instrument may be configured for reflection or transmission with divergent and focusing optics, an automated XY stage, and 3 different radiation sources for a wide range of experimental configurations. 2 separate detectors provide fast, 2-dimensional data collection. The older XRD has been reconfigured into a dedicated environmental controlled instrument where experiments may be conducted in a variety of atmospheres with controlled humidity and atmosphere within the 5 degrees C to 95 degrees C temperature interval, and temperatures that can range between minus 196 degrees C to 450 C. The field emission scanning electron microscope provides a 1 nanometer spatial resolution at 15 kV and 1.5 nanometer resolution at 1 kV for superior imaging capabilities. It is also equipped with backscatter electron detector for compositional imaging, secondary electron detectors for surface topography, transmission, cathodoluminescence, and electron backscatter diffraction. It is coupled with an X-ray microanalysis and imaging workstation that automates the stage control and image acquisition for unattended data collection. The polarized light microscope is capable of both transmitted and reflected imaging using white light in plane and cross-polar modes. The stereo microscope is unique with its single optic axis and chromatically corrected optics for high-resolution color-correct imaging. Both instruments are coupled with high-resolution color video cameras with a dedicated image processing and analysis workstation. The environmental scanning electron microscope has an extra-large chamber to accommodate large specimen imaging. Being an environmental SEM, one can condense water on a specimen to investigate material-water interactions in real time. It also operates in a low vacuum mode, so specimens do not need to be coated for examination. This instrument is coupled with an X-ray microanalysis and imaging workstation and is used for quantitative microscopy and characterization of cement clinker for standard reference materials and cementitious materials for our hydration modeling.
The large universal testing machine is used for flexural bending measurements of FRP retrofitted concrete, as well as for compression tests of concrete cylinders used in the 3D printing project.
Welcome to the Additive Construction Laboratory. The laboratory is home to our concrete 3D printer seen in front of you. The printer is built on an ABB IRB 6700 platform. It is a robot arm with a 3-meter reach mounted to a 10-meter long track. The robot is integrated into a wet mix grout pump, which we use to mix dry material with water, which is then pumped through this yellow hose all the way up to the end, the nozzle of the concrete, and that is how we create our structures. The structures we create in here are used both for structural testing and material testing. The objective of this lab is to understand the relationship between the material properties and the printing performance. One way that we do that, we have in this lab is a concrete rheometer, which we use to measure the material properties both before and after they come out of the nozzle. Future upgrades to this lab is a 2-component active mixing nozzle shown here, where we will mix an additional component to the concrete to create a set-on-demand effect that will improve the printing performance of our printer. So we see here the robot is moving to its first position. The robot is going to print a series of movements, and you have to imagine a mortar coming out of the end.